Hello, and welcome to one of the weeks. I'm not sure what week it is at this point. I think week 9 of reproducible research in R. So this course is being taught at LSU, and also one lecture per week being released online via YouTube, where you're watching it right now. So today we're going to talk about dependency hell. That's the topic. So for the reading for this week that we'll discuss with students at LSU, we'll be talking about specifically Docker, which I'll go over in the later part of this lecture, which is a sort of way to get around dependency hell that I don't think a lot of scientists have really fully utilized the capabilities of, and myself being one of those scientists. I only sort of intermittently release Docker files for reproducibility, but I'm trying to get better about it. So let's dive right in. So first, I'll just sort of talk a bit about what dependencies are. And so we've gone over a little bit about dependencies throughout the course, basically treating them as a liability. And so we've pulled in, for instance, in R, we use packages, but packages change. And so if I have an analysis or workflow that depends on a package, the reproducibility of my results is therefore intrinsically tied to that package and getting that version of that package installed on whatever machine you have. And so, yeah, I think the general definition of a dependency, I guess, would just be those external packages or scripts or other things which your analytical workflow relies on or depends on. And the reason this is an issue is because these dependencies can change, right? And so your code, your analytical pipeline from 10 years ago is going to inherently rely on packages that, if it relies on packages, but it's going to rely on packages that are versions that are potentially out of date. And so that there's been further development work done on that package. And sometimes package managers, so somebody who's pushing forward a code base and developing and releasing new versions, sometimes they don't think about backward compatibility, which means the current version of the code doesn't necessarily have to work with older objects or older aspects of the code itself. And that's especially true in sort of R development as I've seen it. Yeah. And been involved in it. So, but yeah, package maintainers don't really think about a lot of that, the ideas of backward compatibility. And I think the current sort of tech mindset of move fast and break things sort of inherently doesn't consider backward compatibility as a real thing. So yeah, that's a huge issue. Another issue with dependency is that dependencies often have dependencies, right? So this is especially true in R, and it's really, really frustrating, actually. And so you have these basically chained or like this web of dependencies. It tends to be especially true for a couple different situations, one of which being R packages that are referred to like APIs or interact with web interfaces tend to have a fair number of dependencies. Spatial packages tend to have a fair number of dependencies. And then anything that comes out of the tidyverse, because it's just a web of dependencies. So like they released this package called tidyverse, and I'll go ahead and share my screen now because this is part of the lecture notes, which are linked, are linked below for week 9. All right, so now I'm sharing my screen, and on the left we have the RStudio panel with the lecture notes. And in here, I'm talking about dependencies that have dependencies. and I say install packages tidyverse, which tries to install all the core tidyverse packages, which 8 packages. So let's just try to run this. It's going to take a while, so we can just talk about other things. And then this basically gets at the main message is the yikes. And so it's a good habit to get into in order to check your dependencies, to use this. And it's already installed, so it doesn't take that long. To use this this session info command. And that session info command is going to tell you, and I've talked about it in previous lectures, but I'll show you. It tells you what R version you're running, what platform you're on, what OS you're on, as well as sort of standard libraries that your code depends on. And these are largely matrix, like LPAC is matrix manipulation, I believe. But it also tells you what attached packages you have, and then what are loaded but not attached yet. And so now we can call in the tidyverse package, since we already had it downloaded, and we see there's these 8 core packages in the tidyverse. And let's reissue that session info command, where before we had 5 packages loaded via namespace and 7 base packages that are really slow to change. R is not notoriously slow to change, but it should be slow to change because we don't want to break things. And so these ones are stable and guaranteed, not guaranteed, but pretty much guaranteed to have backward compatibility. These 8, there's no guarantee of that. So let's see session info now. Why is it taking so long to run? Wow, and then we can just see that. So that's why I typed in yikes there, is because these are, all of a sudden we have this order of magnitude shift, or more than that, in terms of the packages that are loaded via namespace but not attached currently. And now we have those 8 attached packages. I guess there's 9 attached packages. I don't know, one snuck through the cracks, apart from the sort of 7 base packages. And all of these are essentially dependencies. And so if you use one package, this package, or any arbitrary package of the attached forms from tidyverse, is likely reliant on some other package that is in this list of 45. So that's just a way to sort of concretely identify changed dependencies as an issue. And the last point that I'll go over about dependencies is that dependencies can be dependent on your operating system. This doesn't happen too much within the R universe, but it happens routinely outside of the R universe. And a lot of the problems where it rears its head within the R universe are because of some back-end library that the code relies on. So things like geos and spatial data analysis things and libraries can sometimes be OS dependent. I think I given an example. RStan has a C++ backend and requires weird sort of finessing and installation instructions in the backend, which differ across operating systems. And so you can build up a nice, completely reproducible analytical workflow, but if it depends on some other library like RStan, all of a sudden you're placing the burden on the user to download and install all those dependencies, and the burden on the developers to make sure that those dependencies are backwards compatible. So even the sort of most beautiful reproducible code can actually break down and be unreproducible as a function of dependencies. And that's probably the majority of where code reproducibility goes wrong. Some people just keep their data in code and they don't release it, but even when you do, I think Dependency issues are probably one of the main sort of underlying issues with regards to the ability to reproduce analyses. Yeah, it's like the main one, at least the most common. And so this lecture is entitled Dependency Hell, which is a silly term, but is like super accurate if you've ever gotten into it. Gotten into that dependency hell. And it's just a sort of colloquial term that refers to that sort of dependence on different dependencies. And so chain dependencies, where one package depends on another. And it can take a few different forms, I think, that I go over here in the lecture notes. So let's start for point 3, just because I've talked about it the most, I think, so far. So that's dependency chains, and that's when a package that so let's say like you write a beautifully analytically reproducible code set that's like solid and only relies on one package. If that package relies on like 20 other packages, that can pose a problem, because all of a sudden you're sort of betting on those other packages being there and being properly maintained. And so R packages with updates of R sometimes go unavailable, right? And that's because they're removed from CRAN, which is the centralized repository for R packages. And this removal tends to happen because of issues regarding like long time to updates, or sometimes errors in the package that are just uncorrected. But it can happen to really sort of well-known packages. So I just got an email the other day about RVest, which is a text mining or web scraping utility, basically, that's maintained by people at RStudio, potentially getting archived, and how that would affect code that I had existing and the packages I built. And that's all like was a sort of not a misunderstanding, but it's like it's sorted out now. But still, like if it can happen, it doesn't just happen to small, rarely used packages. It happens to big packages as well. And it doesn't even matter if it happens to small packages. Like let's say you use like the Beyonce color palette. There's an R package that has color palettes that are based on Beyonce photos of Beyonce, which is fantastic, and that's a fantastic idea. But if your code relies on one of those color palettes to make a graph or something, and that dependency goes away, like your graph is unreproducible, which is not ideal. So something to keep in mind. Another way that you get into dependency hell, so moving up to point 2 on this list, is just having many dependencies. And that's where we suffer. So I've definitely written code where I call all my library calls at the top of my code, because I think that's good practice. So if I write 1,000 lines of code below it, I call everything in at the top, so that you know exactly what you need in that workspace before you start running the analysis. Cat's meowing at me. It's a sad meow. She's eating food and meowing. So yeah, packages like DevTools have a ton of other dependencies and will take a long time to install. And that's a way you can get into dependency hell as well. And then what was the first one? Packages or some software reliance, specific versions, that's killer. And so this happens, I've run into it way more outside of R than inside of R. So Python is like a notorious example of this, because they had like some packages ran on like version 3 above, and other packages were back on like version 2, and it was just a sort of shit show, if I'm being honest. I never got like that into it, but yeah, that's rough. Because then like if you have a machine that you have the most up-to-date version of the software, and in order to run other software or run an analytical pipeline from another researcher, you have to downgrade your software. That is going to inherently just present challenges to you and potentially some issues downstream when you want to run other analyses or just sort of allowing coexistence of different versions of the same software. And that one's really irksome. All of these are irksome. And so I think now we'll go into how to avoid dependency hell, because it may sound silly, but you're going to get into it. If you already haven't gotten into it, it's a thing. And so I think to really root this, or like to drive the point home, even in just the R universe, there was a study in 2014 that found the occurrence of errors in CRAN packages over a period of 3 months, that's super duper short time scale, resulted mostly from updates in the other packages dependencies. And so software is built on top of other software, and you pull out one of those bricks and the tower falls down. If you were to remove RCPP, this package that I'm highlighting down here, it, let's say, just broke, or like it was just deleted off the face of the earth, all that code was just lost, which I hope never happens, you would break so many other R packages. That package is one of the most depended on packages within the R ecosystem. And so, and nobody's paying the person to develop and maintain this package, right? I think it's Dirk, and I don't want to mispronounce his last name, but it's a fantastic package that I'm not sure he's actively being paid to maintain it. So this is a lot of volunteer effort, especially within R. And it's rough. Okay, so now I've painted the picture of dependency hell, and we've talked about dependency hell. And now we want to talk about how to avoid dependency hell. We don't want to get into that situation. And there's a few, I think I give 3 or 4 ways. And the clearest and most simple way is fewer dependencies. If you can sort of adapt an existing function, if you're only using one function from a package, copy and paste the code over, adapt it, write it, roll your own. Like it's better in the long run for the reproducibility of your results. Yeah. I know it's silly to say like reinvent the wheel, and I'm sure that many people would disagree with me on this, but in terms of long-term like reproducibility, if you're not using that many functions in a package, it's better to just copy them over, as long as they don't rely on like a web of functions that are also within that same package. So yeah, I think I'd consider reverse engineering it, checking out the source code, all that code from every function and every R package is available. And they version it on GitHub as a mirror, so you can view different versions of the same code base. Yeah, and I linked to a couple articles. One is the idea of the sort of minimalist tiny verse. And there's some people that, like, when I was researching sort of to write this lecture, some people are like, dependency hell is real, but let's not worry about it. And I'm more on the side of dependency hell is real, let's worry about it. Because we probably should, in order to do good science at the rate that technology is sort of advancing and these packages are being developed. We need to really think about reproducibility and dependency management. So the second sort of tip for getting around dependency hell is in your code, be very explicit about which packages you're using and which versions you're using. And so here, I think I've talked about this previously, but all packages should have some sort of semantic versioning. And typically that comes in number dot number dot number, where numbers correspond to major version, minor version, patch. We can see that down here. Dplyr, for some reason, is still in 1.0.0. It's the first major version, and there's been no patches or minor versions. I think it's crazy. Maybe I had an out-of-date version or something. Meanwhile, Tibble, which came out later than dplyr, is already on major version 3 and patch 3. So it's pretty arbitrary. But you can specify which package versions you want when you install within R. And so that is generally good practice. And so instead of just making a bunch of library calls at the top of your document, you can actually specify exactly which versions you want to install. And I think I go into how to do that. Yeah, so I just arbitrarily, I store this as cran URL and then as a string, which contains the URL to download the R package vegan from CRAN's archive. And so they maintain all the existing versions of the package. So you can download version 1.0. And so here I specify that of vegan, I want major version 2. And so 2.0.0. And then I can use that using base R and say install.packages. And then I hand them the URL. And that's a obviously sort of just clear way to install the exact dependency and version that you need to run your code. Oh, and that's actually a really early version. So it's 2011. And so if you had an analytical pipeline from 2011, or you're using the vegan package, which is like a package for community ecology largely, then yeah, you'd have that version. And so if I wanted to run that same code today, the vegan package has probably changed a fair bit since then. I know it has actually. Yeah, so you want to specify a version. So I'm scrolling ahead. All right, I talk a little bit about Packrat. Yeah, there's a super clear downside to this, in that downloading the vegan package from 2011 replaces the vegan package that you have currently installed. And so all of a sudden you have this like time slice of packages where you've just replaced the 2020 version of vegan with the 2011 version. Not ideal, because that breaks other dependencies, sort of forcing you into dependency hell, which is something we're trying to avoid. Yeah, but there's a way around this, which I go into in the sort of but later in this lecture. And that's about containerized builds. And so containerization is something that's becoming increasingly popular for people developing code and developing applications that build on code. I'll go into that later. I think now I'm going to talk about a simpler fix, which is maintaining package versions using a service. And I think this is the last. Oh no, that's the last. So what I mean by service is an R package that basically maintains versions of other R packages. And so this was a cool idea that started as Packrat was the initial name for it. And I don't even think Packrat is maintained anymore, which sort of gets us into a clear limitation of this approach, and that it relies on maintainers to continue to maintain packages. But sort of the Packrat project is based, and it's been morphed now into our ENV, or our environment. But the original idea of Packrat was you set up a project, you download all your dependencies, all your package dependencies, and it stores them as like an image, so it keeps them all together. And as long as you keep them all together, then you can get the exact workspace with all the packages and the exact versions as below across OSs and through time. And so it has a pretty nice user interface where you issue the R command init and then call your project something. And then once you do that, basically, it starts recording whatever packages you're installing. And so when you submit, like when you type in like install.packages in R, it's going to like store that information. And then you can take a snapshot in Packrat of that function to sort of copy the existing state of your R workspace with all the different package versions. So basically, it takes this like session info with all the loaded packages and boxes it up really nicely to be shipped off to other OSs and other computers and other times, which is pretty. It's pretty nice. It's a pretty nice way to get out of dependency hell. And I say here it's fairly reproducible. The only limitation on it would be if Packrat was all of a sudden not maintained, because that's not ideal. Or if you had OS issues in terms of installing dependencies of existing packages. And so if a package relied on something that wasn't installed on the host OS, regardless of what it was, then you'd run into the same issues, which is a clear problem, right? Because ideally, you'd want your code to be reproducible across OSs. And so a Windows user, a Mac user, and somebody using like some bleeding edge, ridiculous Linux distribution should all be able to run the code. That's the goal. And then the last idea, or the last way to get out of dependency hell, is to basically build your operating system from scratch. And that's a weird way to put it. I might like change that before I release these lecture notes, but probably not. Because you could completely build your OS from scratch, and that would be something like a virtual machine. So I offer that up as the first idea. And a virtual machine, basically, imagine it as like a window on your computer where that window corresponds to a virtualization of another operating system. So I'm running Linux right now. If I wanted to run a Windows operating system, I could do it using a virtual machine. And so what that would mean is like basically I have a window open that's running a entirely independent, a mostly independent Windows operating system in a box. But around that box, I still have access to my Linux operating system. And so basically, I'm relying on my computer resources to be cool with running two operating systems. That sometimes is a bad idea. It's not always a bad idea. Operating systems actually are not that bloated. And I say that as somebody who at University of Helsinki was handed their de facto Linux operating system, their one that they use, and it was like 4 gigs or something, because they had like every version of every package installed on that shit. It's ridiculous. They had like 30 text editors. I quickly installed my own Linux operating system and didn't deal with theirs. But operating systems can be bloated. They can be heavy, and you don't want that. So there's a second option, apart from the sort of bloaty virtual machine, and that is to use Docker or some sort of platform that allows containerization. I'm seeing, oh, here we go, okay. So I'm looking at the flow of the notes. Yeah, so a lot of virtual machines use Linux OS because it's hard. I mean, in order to run a Windows VM, you would have to have the Windows operating system as like an ISO image, or as you have to have access to that proprietary operating system. The same with Mac OS. And so Linux operating systems tend to be the most often things that you would use a virtual machine for. And you can also set up the image as persistent, which, again, reminder, I have 10 or so or more by this point, because I think 30 people are registered for this course. Flash drives that have a persistent, meaning files can be created, saved, deleted, operating system as a flash drive. So if you want that. And I guess that's sort of like a third option, but I mean, like, you don't have, it's basically the same thing as a virtual machine, right? Like, your code is openly available. It's not like you're going to mail somebody a flash drive, but you essentially want that flash drive to be there, in a sense. And virtual machines are one way to get that flash drive there, if that makes any sense, or if I'm just going crazy. But separate, like keeping an entire OS on top of your existing OS is memory intensive. And so I was wondering, I've talked a little bit about why this isn't normal. And it's not normal because ecologists be ecologists, or scientists be scientists. They're more focused on the science than they are the reproducibility of the code. But also because it is a massive, it's a pain. And it's a pain because it depends on, like, so if I release a virtual machine image, is often what it's called, and say, like, yeah, run this code on this, like, the virtual machine image depends on the virtual machine software that you'd be running. Oftentimes, it's clunky. It's hard to like share that because sometimes the files are rather large, and so it sort of becomes a whole thing. But then there's Docker, and Docker is what I'll spend the rest of this talk on. And so Docker is a little bit different from virtual machines in that it focuses on containerization. And containerization, so Docker is basically a tool that sort of allows developers to like deploy code or applications within containers that run a specific host operating system. But it doesn't partition memory in a way that's completely independent from the host operating system. And so it just sort of, imagine it just sort of laying on top in terms of memory. So if you have this box of computer memory, a virtual machine is like, I'm going to take a chunk of this box and I'm going to partition the memory and say, these are the resources for the virtual machine, and these are the resources for the host OS. Docker doesn't do that. They share resources, and by doing this and by doing a bunch of other things, it makes Docker containers really lightweight, and so they should be able to be run on most all computers, which I think is a huge benefit. And containerization has become incredibly popular, especially in recent years. Especially like on like server environments and things like that, where like dependencies are just inherently an issue when you have so many users trying to use the same computer resources. Containerization is like pretty essential. I'm gonna take a short break and then we'll come back and I'll talk all about Docker, which I waffled on discussing in this class because I thought it might be a little bit too niche. But I think it's really, really useful, and I'm a strong sort of advocate of using Docker to basically like solve dependency issues and dependency hell. And so with that, we will be right back. Hey, and welcome back. Take a short break. Gonna reshare my screen. All right. So So now we are back. Let's clear out the terminal. And actually, I thought I remembered I was going to use the terminal from RStudio. All right, so I have a clear terminal, and we can get going on Docker. And so there's actually a fantastic Docker tutorial available here. So docker/curriculum.com, and that's hosted by the Docker people. And I'll just leave that there for now. And so that's probably, if you read through that, it's way more exhaustive than what I'll go over here. And actually, like, I'm not even really going to go over like the formation of Docker files. I'll mainly talk about using existing Docker images. And so Docker has, this is a good like segue, Docker has a lot of verbiage and language around it, which is a little bit confusing. And so you have a Docker file in order to create this container. So think of a container as similar to a virtual machine. It has an OS, and it has all of the essential things needed to run a specific code. And so the Docker file is a text file that gives shell commands that install and set up the things needed for that container. An intermediary step between a Docker file and an actual container is the Docker image. And so these images are like the resulting build from the commands in the Docker file all put together. But a container has to be like actually like running on your machine. It's the realization of, a container is a realization of an image, in my understanding. And so you can pull these images, which is super duper useful. And so Docker images can be pulled from a place called Docker Hub, which is similar to GitHub, except it just hosts Docker images, which are just these beautifully pre-built, I don't want to call them operating systems, pre-built containers that contain the essentials needed for analyses. And so there's many, so our base has their own, or maintains a Docker image. And so you can issue this command. So this is a shell command that's sort of, so sudo it gives you sudo access. Docker, which you'll need to install Docker. And so I'm just going to assume that you will do this on whatever OS you are on, but Docker is agnostic to OS operating system, so you should be able to install Docker and get it set up. Some of these commands may be specific to a Linux operating system, but these should largely not be. You might have to tweak a little bit of it. And so similar to like working with GitHub, right? So like if we were working with GitHub, we would use git pull and then something. And here we can see it's actually really similar in that it's, instead of git, it now says docker pull something. And the something that we're pulling is, for this example, is the latest version of R. No TTO because it thinks that I'm trying to run it. All right, so we'll issue that in the terminal and then type in password, and it's going to download and pull the R-based latest, which I think is built on top of a Linux operating system or Linux kernel, but we can explore that. I actually don't remember. And so this is working. It's downloading. Excuse me. And so similar to Git, we sort of interface with Docker using the Docker command. So Docker is that base command. And it can tell us a bunch of things. Like it can tell us which images we have installed. it can tell, oh, so that's this, is I'm looking for installed images. We can also look at what containers are actively running, right? So there's nothing to stop you from running like 20 containers at once. So if you were deploying like a web app or something like that, you could do that in a Docker container, and that could just be continuously running in the background. But you could also be deploying something else, and that's in a container. And so to check the existing running containers, you would say something like that. And so this shows all the information, or all, okay, it's getting done. And so I'll run these commands once it finishes. I think my internet's just slow. It shouldn't be this slow. But not a huge deal. Yeah, so this top command will list all containers, active and inactive, that have been run or that are running, either way. This will list all the images that you have downloaded. And then you can remove containers and you can remove images. It's always nice to have like images sort of flying around, although I don't have many images on this machine. I think I have more on my lab machine. This is the home machine. Oh, it's not like halfway done. So let's just open a terminal and I can show you some of the output of these commands. All right. So let's see what I've been running. Nothing. I have no containers that are active, and it's been a while since I've run it. Maybe these are only active containers. But we can also use that and use the images command and see what Docker images I have installed that I could run in containerized builds. And so I'm going to switch to the default. And I hope that's not too small, but it was really cumbersome the other way. And it's not really important what these are. And so our base I downloaded like 6 weeks ago. And then previous to that, it's been a long time since I've done anything on this machine with Docker. So it's 3 years ago and 4 years ago. 4 years ago where I pulled the image for Hello World, which is like the base one that just like prints Hello World. And then I used Selenium, which is a way to interact with websites in a programmatic way. Not to scrape, but to actually like click on stuff, quote unquote, and do other things. Yeah, that's from like a generative art thing that I was playing around with for a little bit. And then Julia is a developed programming language that is pretty awesome, way faster than R, and pretty sweet, but also used for statistical programming. It's pretty awesome. You should check it out, Julia. Let's see what version I have. Just installed. Oh, it is installed. It's a liar. My computer's a liar. I was just using it the other day. All right, so this finished installing that image, or pulling that image, that our base image. And now we can issue commands to actively run that image and turn it into a container on this machine. And so here I use the Docker run command. And so to look at Docker's other commands, you can just say Docker help, and you can see all the actual sort of verbs, the action verbs you can give to it, which is you can say build. And so if you have an image, if you have a Docker file that you want to build to an image, you say Docker build, and you say build this image. And so if you're, and this is incredibly useful if it's potentially, it is more reproducible to have a Docker file than to rely on somebody else's Docker image, right? So I think releasing a Docker file that has all of your dependencies and versions of your dependencies specified within the Docker file is better practice than just like pulling down a Docker image and building off of that. And so being comfortable with this build command is important. But you can also maintain your Docker file and your image via Docker Hub until the point where Docker Hub no longer exists. And then there's other verbs, so to create a new container, blah, 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 list images. So that's one we've already used. We use that above here, sudo docker images. And then basically ways to load and kill or interact with Docker images and containers. Yeah, okay, so we have images installed. And let's say we want to run the R-base image that we just pulled. These other flags do other things that help us interact better with the R-base, but they're not that important. You can run it without those flags and you're fine. So yeah, let's copy and paste this down below. And so this is a little bit of an odd thing because we're using this in our studio. And we're going to basically be working with a version of R that is not the version of R that is our studio. And now that is confusing, but I'll show you what I mean by that. So now we get sudo docker run, and now we're in this R environment, right? Boom, we're in this interactive R environment. It's version 4.0.2. And we can type in normal R commands. We can make a vector A of 1 through 10. We can remove A. We can collect our garbage. But we're in R and it's interactive. But this is a different version of R. We're in a container. And so this is version 4.0.2. If we hop in the console, we just issued session info earlier in this lecture. We're using version 3.6.3, right? So we're basically, our studio and this local machine, my computer, is running version 3.6.3. My computer is also within a containerized version running version 4.0.2, which is pretty sick. That's pretty awesome. And you can imagine how that gets around a lot of the issues in dependency hell. It gets you out of that. So we can quit and leave the workspace and we're back. And then we can use something like that just to list the existing running containers and nothing's running because we just exited out of it. We don't have to issue this. Yeah, so this says, oh, you have to issue, so if you want to use stop to stop a container, you have to specify the running containers, but none of our containers are running, right? So we can look at that with the PS. Nothing's running, we're good. And then we can look at our images again and say, created 22 hours ago. And this one was created 6 weeks ago. These differ slightly in size. So maintaining these images is really important. And then we can remove images. And so let's say we want to remove, I think this will remove the most recent one. I'm actually not sure. What is it doing? It seems right. I don't know. But yeah, there's RMI and then RM, which it should say. It doesn't list in there. Where is it? Oh, it just says RM. But RMI is also a thing. So let's remove it. No such container R-base. That's a lie. You're a dirty, rotten liar. And tab complete doesn't work. I guess it's not a container. It's just a an image at this point, so we don't have to worry about that. And we can use that to remove all stopped containers. And so that will just remove, that doesn't even tell us, but yeah, it removed nothing. So I got reclaimed space of 0 bytes. You can start to understand how this works, right? So you can either write your own Docker file, which is a low-level list of instructions to build up a Docker image, or you can pull a Docker image down from an existing repo on Docker Hub. And then you can build that image into what is essentially an independent OS that sits on top of your existing computer resources that is specific to doing a task. It has all the tools you need in a little box. And then you can issue commands and get things in that little box and run analyses in that little box and get out of dependency hell. So hopefully this has been enough to like whet your appetite and to get you interested and get you thinking about Docker and get you playing around with Docker. And so you can go to Docker Hub and mess around with it. Just like, I'm now sharing and going to Docker Hub. I'm down in, I didn't sign in. But it's awesome. And it has a lot of sort of existing like functionality and apps like built on top of it to definitely be worth perusing and playing around with. And so I'll probably go into more detail on Docker and play around with it in the other lecture with LSU students. But hopefully, yeah, you're excited by this, and this has been a talk on dependency hell and how to get around it. And so using things like packrat, not relying on dependencies, and being explicit about package versions are really clear ways to make sure that your code is not just reproducible right now, because that's not important. It's that code is reproducible years in the future, which is far, 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 far more important. So yeah, thank you for tuning in, and take care.